It doesn't consider that you only need 90% of the clicker points to get 100%, so that's going to be scaled up. And then the other thing is the final exam. If you show me you mastered exam 2 material by the final exam, 3 material by the final exam, then I'll go back and give you half credit for those topics that you've mastered. Right, so that's not reflected now. That's additional growth that you can have in your grade. Did you guys find the exam wrapper for exam 1 valuable? The process of doing it. Yes. Raise your hand if you found the process of the exam wrapper valuable. Okay. Raise your hand if you did an exam wrapper for exam 2, even though you didn't get any credit for it. So why are you guys in college again?
My mom forced me.
Nice.
Okay.
Truthfully.
Stop, Amber.
So, all the ones I mostly missed were on the multiple choice, and I couldn't see what I got wrong. So I need to become the office hours and maybe show what.
So the answer key's posted online. I had multiple requests for it.
Okay.
So it's up, it's online, it's under resources or content, I can't remember which, in Blackboard.
Okay.
I posted it just for that reason because I wasn't going to go email you every question you got wrong again. I wanted to find a more simple way, and I had multiple students suggest just post the answer key. Okay, but please when you go through it, don't, I would identify which ones you got wrong first, and then go back and try to figure out what the right answer is. So like you did for the exam wrapper. I made you guys do that for a couple of reasons. One is, if you're discouraged, to bring you back from the edge of discouragement. Second reason is for you to actually work on the things that we identified you did do as well as you wanted to on. And then the third is grade-wise, to make it kind of all come together. So you still have the same capacity to increase your grade on exams 2 and 3. I'm just not doing the formal exam wrapper. But please, I saw almost every hand go up that they found that experience valuable. Please use that as a tool, not just for this class, but any class. You take an exam, going back, and instead of just putting an assignment like, that sucked, I'm not happy with that. Use that as an opportunity to figure out where you're not doing as good as you can, and then improve on that. Ideally, we do that before the exam, so then the exam reflects your utmost ability. So I'll announce in a minute here, but my Friday's office hours are being replaced by an exam review session. So I'll talk about that in a minute. So let's get into it. I have 11 people with the correct answer and most with the wrong answer.
Fix it. Now.
What's the most simple definition of a combustion reaction? Is anyone pretty confident in their answer? Deanna? Oxygen and?
It has to have a fuel and an oxygen.
Yep. Simplest chemistry definition is we have to have a fuel, something that burns, and it has to do it with oxygen. And later this semester, we're going to talk about that actually is a redox reaction. We're transferring electrons in that reaction as well from another element to oxygen. So, is A a combustion reaction? B? No. Yes, yes. The only one that's not a combustion reaction is B. Okay? So that just helps us frame the discussion a little bit when we're talking about combustion reactions. So why is B not a combustion reaction? Love?
Because there's no oxygen present, that's why you cover the oxide present.
We have to have O2, molecular oxygen, in order for it to be a combustion reaction. Alright, so let's then think about what happens to every component in the reactants. Granted, we saw the reason I think that most people answered D is because we're used to fuel having carbon in it. This fuel doesn't have carbon in it. We don't have CO2 and water as our products. But we don't have to have that in order to have a combustion reaction. But I want you guys to fill out in the worksheet question number 1. Do that with your neighbor. If you burn a fuel, you burn any molecule in a combustion reaction, what is it that happens if your fuel does contain carbon, hydrogen, and oxygen, write where we're likely to find those. Anyone need a mark sheet? All right, I want to hear from 3 new voices this morning. What happens to all of the carbon in your fuel source? What's that, Joe? Yeah. So if we do a combustion reaction, we burn something, if the fuel has carbon, we're going to be generating carbon dioxide. A new voice. What happens to all the hydrogens that exist if we're doing a combustion reaction? Amber? Great. Generates, used to generate water. All those hydrogen atoms end up in water. What about the oxygen? Let's look at one particular fuel. This is, it fuels many fights on Friday nights as well. This is ethanol, ethyl alcohol, or component of vodka, beer, all those kinds of things, right? So this fuel has oxygen in it. In order to burn it, we also need some O2s and a balanced reaction between those, right? So we just said all the carbon ends up in CO2. And there's exceptions where if it isn't hot enough and there's incomplete combustion, we end up with carbon monoxide. We're not focusing on that today. Yeah. All the hydrogen ends up combining with oxygens and makes water. And then where do the oxygens go? Where do the oxygens go?
Well, they kind of go into the end results of carbon dioxide and water.
Sorry, this is a terrible carbon dioxide because it's not linear. It becomes part of both products. Or if we have other products, right? We saw sulfur trioxide as one of the products. So what I want us thinking about is accounting for where each element ends up. For carbon and hydrogen, it's pretty straightforward, right? This is the only place we're going to have our hydrogens is in water. The only place we're going to have our carbons is in linear carbon dioxide. But oxygen ends up in multiple places. So your pre-class quiz for Friday talks about combustion reactions. And it says if we know how much carbon dioxide and water we generate from burning a fuel with carbon in it and hydrogen, how do we figure out what the formula was for that initial reactant? So that's going to be a problem like this. Can I get 2 volunteers to read? And I'll just start a clicker question so you guys can read it on your phones too. Can I get 2 volunteers to read out loud, one for each paragraph?
I'll read the second one.
Okay. I have someone volunteer to read the first one. You can read it on your phone if that's easier, or your computer.
Dynabol is an anabolic steroid used by some athletes to increase their size and strength of their muscles. It is similar to the male hormone testosterone. Some studies indicate that the desired effects of the drug are minimal. Side effects include sterility and increased risk of liver cancer and heart disease. Keeping most people from using it, it is not legal to use in most cases. Other anabolic steroids such as trinolone are legal for most uses.
Amazing pronunciation for your first time through that. Nice, Jason. All right, great.
You have discovered a dry white powder in the locker room, and you wish to use combustion analysis to determine if the substance is Dynabol or its illegal alternative, trinolone.
So this is what I want you guys to picture. We have an unknown compound. This is actually legit what chemists do in order to determine the identity of a substance. We have a couple of different ways of looking at it. One is mass spectrometry, which I'll talk about in a second. The second one is combustion analysis. So in combustion analysis, we'll go ahead and we'll put our sample into a furnace. In particular, this substance, if it's Dianabol, would have carbon, hydrogen, and oxygen. We're not sure what the ratio of those would be. We're going to supply that furnace with excess oxygen. And then we have two traps over on the right side that as we heat up our sample, it undergoes a combustion reaction. Any hydrogen that existed ends up in water. Any of the carbon that existed in that compound ends up in CO2. And as it passes through, there's two scrubbers, one that will absorb any water, and we can weigh this before and after this mix is passed through. So we can weigh how much water is absorbed. CO2 and any other molecules will pass right through. CO2 then will get sucked into this trap over here. Same thing, we can weigh it before and afterwards. We can determine the mass of CO2 produced. So we put a known amount of material in here, 20 grams, whatever it is, right? We know how many grams of water are produced. We know how many grams of carbon dioxide are produced. If that fuel, that combustion material, also contains nitrogen, then most likely that comes out as NO2, and some combustion analysis can actually analyze for nitrogen as well. And then all the excess oxygen, right? We didn't burn all the oxygen because we put in excess, so that's all going to pass right through. So then what I want you guys to be able to do, and what we're going to be working on in class on Friday, is we're going to have to determine the molecular formula of the original thing, the unknown that we combusted, by knowing how much we put in the first place, how much CO2 was produced, and how much water was produced. Think you guys have an idea of how that's going to happen? Talk to your neighbor for a second and try to figure out how you can identify the ratio of carbon, hydrogen, and oxygen in the starting material by knowing the mass of carbon dioxide and water in the product. Go ahead and take a minute and try to discuss with your neighbor how that might work. All right, is someone willing to share what their group discussed? How might we take the information that's given here? I don't need to know the exact calculations, and we don't need to know an answer yet, right? But what approach might you use in order to figure this out? Christina?
Could you put like 14.765 over like each of them and your ratio, like a fraction?
Okay, so one thing that I want to use that to describe, to point out, if this is how much mass we started with, and this is how much mass we ended with, what's wrong? They don't add up, right? So what's missing? We added oxygen, so we have a whole bunch of O2 molecules, but we don't... Could we figure out how much O2 was added to this reaction? Yeah? So the sum of these and the sum of this and oxygen should be the same. So we could actually figure out the grams of oxygen that were added to this reaction. We could back that up. All right? So how do we use these masses to figure out the formula, or at least the ratio between carbon, hydrogen, and oxygen? Thoughts? Love?
Well, first you want to find the moles of each of them.
Moles of each what?
Moles of each of the reactants. I mean, of each of the products.
Okay, so if we know how many moles of carbon dioxide, how would that help us?
Well, because when you look at CO2, the ratio between carbons and oxygens is 1 to 2. So you know that there's there should be double the amount of moles of oxygen and they're of carbon, so you can basically set up a stoichiometric.
Great. And so what Love is pointing out is that we have more stoichiometric ratios, more unit conversion ratios available to us than we might have seen before. For every mole of carbon dioxide, how many moles of carbon are there?
1.
Every 1 mole of carbon dioxide has 1 mole of carbon in it. That tells us that we know exactly how many moles of carbon we have in our product. How many moles of, what does that compare to the moles of carbon in our reactant? We have a certain number of moles of carbon in the product. The only place that those come from is our fuel. So that means that every carbon in the product, if we find out how many we have in our products, we can figure out how many we had in our reactants. We do the same thing for water. If we figure out how many moles of water we have in our product, how does that relate to the number of moles of hydrogen we have in our products? Is it the same?
There's double the amount of water.
H2O.
Oh, yeah.
Oh. So that means that we have 1 mole of water as a product, then that means that we have 2 moles of hydrogen. We know that all that hydrogen came from the reactant, so now we know exactly how many moles of carbon we had in our reactant, exactly how many moles of hydrogen we had in our reactant. So we can figure out the ratio between those two. The thing that gets more tricky is what about oxygen? Because we have excess oxygen, but as Christina pointed out, we can figure out how many grams of oxygen we have in this case. So there's a lot of calculations. You guys will have in your pre-class quiz for Friday, you'll have one that just has carbon and hydrogen, so if you can follow what we just did, or watch the tutorials that they have, I think there's tutorials related to this, then you guys should be able to get through that for the pre-class quiz for Friday. That first part will only tell you the ratio of carbon to hydrogen. It won't actually tell you the exact number. So there's another fancy piece of equipment called a mass spectrometer. What it does is it literally takes individual molecules. It bumps a hydrogen off to give them a charge. So say ethanol is what we're looking at. It would push it into a negatively charged version of itself because it lost an H+, and then it puts it in an electric field. It zooms it up, it speeds it up because now it has an electric charge. So it shoots it with a certain amount of force, and then it forces it to bend around a corner inside of a little instrument. And then how far it bends is based on how heavy it is. The heavier it is, the less it's going to bend. The lighter it is, the more it's going to bend. And they detect where it actually hits the side wall. And they can backtrack how heavy it is, what the exact molecular weight of that compound is. Individual molecules. Mind-blowing. So that's the mass spectrometer, and with that you can figure out what the molar mass of the compound is. And that is something we use in order to figure out the molecular weight. Does anyone remember the name, if you've done this before, the name of the ratio of carbons to hydrogens and oxygens? The whole number ratio of those to each other? Similar to the molecular formula.
Empirical formula.
Empirical formula. So if we just know the ratio of carbon, hydrogen, and oxygen, that's empirical formula. For glucose, that's CH2O. We'll be talking more about that on Friday. But I just wanted to give you guys a little frame of reference for what you're going to be doing for your pre-class quiz for Friday. So for today's class, I want you guys to be able to, we're going to be working some more with limiting reagents. I want you to be able to predict yield from a balanced chemical equation with different amounts of reactants, and then to calculate how much of each reactant we might need in order to produce a desired amount of product. We'll be talking about the Haber process today, and my animations are out of order. Talking some more about percent yield, identify misconceptions, and then this is the terminology that's used pretty frequently, is calculate the most product we can possibly make given a certain amount of starting materials. So I think you guys have seen that in your homework, right? Where it says, given this amount of two things, how much product can we make? And so it means based on the limiting reagent, how much can we make? I decided that this is a challenging set of topics. So my Friday's office hours is going to be changed into a exam review session. So these are the topics we're going to be going into. Topics of unit conversion. If you don't feel solid in that, come work on this stuff. Stoichiometry, limiting reagents, molarity, and then also some of the combustion analysis stuff we'll do in class on Friday. Can I get a show of hands who might come, and that'll determine what room I'm in? Okay, so it's more than 10 people, so we're going to do this in ETAS 125. I have a very large meeting table there and a big whiteboard. If you're not quite sure how to get there, if you literally walk out this door, it's the corner of the ETAS building right here. So you can come in it from the main front entrance, and then it's just walk right in. I'll have the door propped open, and there'll be a sign outside.
So the exam review session, when is the exam?
Next exam is October 28th, Monday. So it's every 3 weeks for the rest of the semester once we started. It was 4 weeks for the first exam, and then 3 weeks, 3 weeks, 3 weeks. All right. Everyone clear on where we're meeting, what time? The most use you're going to get out of this exam review session is if you have specific questions on these topics. So homework's open, try working on the homework a bit and be like, I'm really getting stuck on this. Or these pre-class quizzes have been giving me a hard time, or this is something we did in class that I don't really understand. That's how you're going to get the most out of it. I will be able to prepare some questions that will help you work through stuff as well. But if you bring questions, it'll help. Okay, I will send an announcement out with the exact location because I might be competing. Okay. We'll figure it out. There's a couple spaces we can use in there. Thanks for the heads up. All right, this is from the worksheet that I handed out to you guys last class. I want you to talk to your neighbor and try to determine why the following statement is incorrect. Here's a balanced reaction, but then the statement in quotes. Why is that statement incorrect? All right, can I hear from a new voice? Why is this statement incorrect? Angel.
Because the number 8 in front of CO2 represents the number of moles, not grams.
What is moles a measurement of?
Quantity.
Great. So this is talking about how many of them, not how heavy they are. So these might be really light, it might be really heavy. The statement might end up being somewhat close to true. In this case, I don't think it does. So if we're looking at the stoichiometric coefficients, we always want to make sure that we're distinguishing between when it's talking about quantity, which is those, versus how heavy they are, which is mass. This is a very common mistake, a very common misconception when you start doing calculations of stoichiometry. So let's just keep that in mind as we go forward. So then how would we make this statement more accurate? Marquise?
Would you change the 8 to 16? Or will it have 16 grams of carbon dioxide?
So can we say... Wait, so say the sentence...
Instead of 8, would have 16. Oh,
Careful. Miracle, what did you say?
Sir?
What did you say?
I said if you put the 16 on the outside, then it'll change the number of
carbon, so the equation has to be balanced.
True. So what is the fundamental thing, though, that we need to change about this statement? Joey?
Change where it says grams per mole.
Right. So we're not talking about how heavy they are. We're talking about how many we have. So we could rewrite the statement saying burning 2 moles or molecules, either one is accurate as long as it's a quantity, of butane will produce at most 8 moles of carbon dioxide. If we have moles in the top, we have to have moles in the bottom. If we have molecules in the top, we have to have molecules in the bottom. So let's go ahead and I want you to write a balanced chemical equation for the combustion of acetylene.
It's not combustion, there's no oxygen.
True. For the reaction between these two. That was a combustion reaction, and then this is another reaction. Okay?
It's hydrogen. No.
So,
Acetylene and hydrogen gas?
ethane's a
and
reaction.
So there should be an and in there.
Yeah, because it was.
So the acetylene solution on heat
I think I'm out of my zone here, but I think acetylene combustion with a torch. Actually, I don't know. Does anyone know? Does anyone weld? When you use an acetylene torch, do you need to have hydrogen gas with it? Or is it a combustion with, I assume it's combustion with oxygen. Isn't there certain welding you can do underwater?
Yeah.
What kind of welding is that?
Yeah, so you can just.
Not O2. Well, there is some dissolved. All right, do you guys have a balanced equation? Does anyone want to write out their balanced equation?
Okay.
Say again? That's underwater? This is definitely a discussion board question. We'll keep it up there, pick it up there. Okay, so Bria has a balanced equation here that says so we have stoichiometric coefficients of 1, 2, and 1. Does that sound reasonable? Does anyone have something different? Could we have 2, 4, and 2? It's not the best version of the equation, so we always want to simplify that down to the lowest whole number ratio between them. So can someone put in a sentence how acetylene relates to ethane based on this equation? Ruby?
1 mole of acetylene will react with 2 moles of hydrogen gas to form ethane, produce ethane.
Okay, and the only difference I'd say there is at most 2 moles or 1 mole of ethane, right? Because we talk about limiting reagents, so it can react with 2 moles of hydrogen if the reaction goes to completion. All right, so now you guys have two quantities of your reactants. What question number is this? 5. Question number 5. We're cruising today. And I want you guys to figure out how many grams of ethane we can possibly produce. Raise your hand if you want a little help. Sam and I are happy to come around and help you get started. Remember, I want to see this written out clearly using unit conversion, dimensional analysis. So if we walk around and just see a number on your paper, we're going to give you a little bit of a hard time.
I remember since it was 60.
It's really important to discuss how the transfer of the mulch or something else.
You can't see. That's the only thing that I hate.
Are you guys pretty good at finding molar masses now?
Yeah, I'm tired.
And calculating them? If you're on your homework or in class, Google it. Don't waste your brain power and your time adding up carbons, hydrogens, oxygens. Just Google it. Find molar mass. Great. People are already doing that. Makes me happy.
Yeah, I got 24.4 minutes.
You're on the right track. I just want you to be able to see.
Oh gosh, I don't. I know we have a TV because I just lost it. Maybe more. Oh, we're meeting Friday. product. So you can buy right. Give me all you back. I have not started on
Okay, we have a lot of people clicked in, so I'm going to leave it open while we kind of talk through it to make sure we're all on the same page for this. So this is kind of more than just a problem, right? There's a couple problems built into this. I wanted to see if you guys are comfortable kind of going from 0 to 100 on this without the steps in between. How did you feel on that? Give me a thumbs up. I'm comfortable with this. To the side, not quite there yet, and down, I need to work on this. Okay, a mix. A lot of ups and a lot of to the sides. So what are the problems that are built into this? Steven, what problems are built into this question?
Converting from grams to moles.
Great.
Back to grams.
Okay, so stoichiometry, basic stoichiometry, converting from moles to grams, grams to moles, back and forth. Okay, fantastic. What else? What's the other problem that's built into this? Amber? Great. You have to find the limiting reagent, because if you don't know that, you can't just say, well, I'm going to assume that acetylene produces as much as it can, and that's going to be our final answer. You have to say, how much can each of them produce? And then compare those. Or you can say, how much of each would I need? Did anyone do the need method? Like, if I used up all of the acetylene, how much hydrogen would I need? Anyone do that? But then what if I asked you for how much excess is left? Okay, so on an exam, let's just talk exam prep. On an exam, look at the next questions. If you have to find excess, then you can decide which one you want to choose. If you don't have to find excess, I agree with you guys. Just go right through and calculate how much product you can make from each one of these, and then compare those two. So if we did this, I think I saw 90% of the class was doing this, so we're not going to go through the entire process. If we start with 25.8 grams, make this bigger, of acetylene, HCCH, over 1. The only comment I had was that a few people, when I was walking around, would just have grams here, and you wouldn't necessarily fulfill the label. And it's really important to me that you show grams of what, and then for the conversion factor of the molar mass, what are the grams that are in 1 mole of a specific thing, right? So just be really specific, fill in all your units. So how much product, how much ethane can we make from, if we used up all of the acetylene? Can I get a number for that, Flo? 49.8 grams of, I got skills in listening. 29.8 grams of C2H6. If we used up all of the 3.25 grams of hydrogen gas, you guys okay knowing that hydrogen gas is H2? I think I saw that on everyone's paper. What are other gases that are diatomic that are always found together?
All the halogens.
O2, all the halogens, and N2. O2, N2, H2, and then halogens. Cl2, F2, Br2, I2. Okay, so if I say hydrogen gas, that's not H. The gas implies that it's a diatomic molecule. All right, how much of this, if we use all the hydrogen, how much at most could we produce? 24.32. Just 2? I hear multiple people talking. So based off of that, which one's our limiting reagent? Limiting reagent because we can produce less of the product if we used all of it up. How would we figure out excess reagent? Mom, do you have a question?
I have a different question actually. Is that, you get that 28, no, 29.8 grams, is that supposed to be the molar mass per acetylene?
Say again? That's
29.8, is that supposed to be the molar mass per acetylene?
no. That's how much. If we use all the acetylene, how much ethane could we produce? So I skipped drawing out all the steps because when I walked around the room, everyone seemed to be pretty comfortable with writing out all the conversion factors and doing the calculations. So once again, in class, Google the molecular weight. Don't spend time calculating it, all right?
Unless you're on a test.
If you're on a test, you don't have that option. So only do that if you're comfortable figuring it out, what the molar mass is. All right, so we answered this question.
No, can you go back to the question you asked?
So then what if I asked you, how much excess is there? I wouldn't have to specify which one. If I'm talking about excess, which reagent am I talking about?
The non.
The one that we didn't use all of. So how would we calculate that?
You could just subtract, 29.8,
So there's a couple of ways.
and then you could convert it back to acetylene.
Yep. Or what's another way? Kayla? So what would we use as our starting quantity in that case?
3.25 grams of H2.
And what are we finding out? What's the sentence we're trying to make?
The excess.
Tyler?
How many grams of acetylene we needed to use up all of the hydrogen gas, and we can subtract that from how much we have.
Did everyone hear that?
No,
Okay, so what Tyler was saying is, with the sentence we want to make is, if we are going to use up all of our limiting reagent, we know we're going to. How much acetylene would that require? So we would have to figure out how many moles of H2 were being used. And then we know the molar ratio is that 2 moles of H2 are required to burn 1 mole of acetylene to react with. And we can figure out that 1 mole of acetylene weighs however many grams. Right? I don't know the numbers off the top of my head. That's not the important part. If we did this, we'd be answering the question, how many grams of acetylene are we going to need to use up all of the H2? It's going to be less than we had, right? Because acetylene was in excess. So then we just figure out, well, how much is left over after we use that much? So, did anyone do this calculation? What's the number?
4.74.
And how many grams did we start with?
Oh, well, I thought that was,
Oh, you already found the difference?
yeah, that's 4.
What's the amount needed?
21.05.
21.05 grams of acetylene are needed to use up all of the hydrogen gas. How many grams do we have to start with?
25.8.
So we have 25.8 grams. We used up 21.05 grams of that. So then can you guys determine how much excess we have? How much was left over? Questions on how we do that? If I said we actually only produced 22.8 grams of can you figure out percent yield? Okay. Those are the types of questions I want you asking yourself as you go through a problem. Even if the question doesn't ask you that in the homework or whatever, ask yourself multiple different questions related to the reaction that you see. There is another question at the top of the next page that I'm going to have you guys do on your own, talking about ethanol. The one I want to focus on now is we're going to talk for the last few minutes, 5 minutes in class, about the Haber-Bosch process.
Oh, yes, that.
Yes. So the Haber-Bosch process is kind of a revolution of chemistry that impacted the world. Some can say for better, some can say for worse. It's a way that we can make fertilizer without having to wait for bacteria to take nitrogen from the air and make it into ammonia or other nitrogen-based compounds. Nitrogen is a very difficult molecule to crack. N2, the molecule, it has a triple bond between the two nitrogens, which means it requires a lot of energy to split those two nitrogens apart. And that means that plants and animals can't directly use N2 from the air. But nitrogen is part of all amino acids. So it's a really important element to have not in a triple bond. So we basically said, well, how do we do this without using extreme amounts of energy or waiting for bacteria to do this? So around 1910, a couple of chemists worked on this and were able to figure out a process to take nitrogen gas from the air, hydrogen gas, and to make ammonia, which is now used in fertilizers. So that NPK on your fertilizer bags, if you ever take a look at them, that N is referring to nitrogen that comes from the Haber process. It's kind of an interesting and kind of a slightly concerning graph. Human population. What do you notice around 1910?
It starts going up.
And there's a few reasons, right? So that's around the time the Industrial Revolution was in this ballpark here as well. But that's about the time where we can start making fertilizer much more efficiently. And so we can support the expanding population without as much restriction for the amount of food that we're making on the land that we have.
And that is not good.
So I think there's a link here at the top of the slide. I'll post these after class that you can go and you can look at for kind of describing some of that process and doing some calculations. So annually, we make lots and lots and lots of ammonia. It's a liquid at, well, it has to be below room temperature. It's a gas at room temperature. But we put it into products that work in nitrogen. We make it into solid forms. Here's the reaction. Take nitrogen gas, we take hydrogen gas, and we make ammonia. I want you to figure out how much nitrogen and hydrogen gas we would need in order to produce 20 kilogram batch of ammonia. You're going to have to figure out both, but right now I'm just asking for N2 gas. So if you were given this problem appropriately on exam, you would not have the stoichiometric coefficients. So what would the first thing be that you have to do to solve the problem? Balance the equation. My animation skills are lacking today. And then can I have someone talk me through the steps, just because we're right out of time? What would our starting quantity be for this set of calculations? 20.0. Make sure we don't lose any sig figs. Kilograms of NH3. Really want to specify that. Would we get rid of the kilo, or are we going to leave the kilo?
We need to be converted into grams.
I would personally leave the kilo. If you don't touch the kilo, it stays there. We just need to make sure that we keep it in mind the whole way through, and that we keep that at the end. You can convert it to grams if you want. 1,000 grams is 1 kilogram. What's our first conversion then? Can I have one volunteer to talk me through this? So we can do this efficiently. One volunteer. Someone have it written out? We don't have to have the final number yet. Gypsy?
For the grams, I got 17.0307 grams.
Is what?
1 mole of NH3. And then 2 moles of NH3, 1 mole of NH3.
So in order to produce 2 moles of NH3, we need to use 1 mole of N2.
And then 1 mole of N2 is 28.0134 grams of N2.
What is it? 20?
28.0134.
So this sentence is saying if I know how heavy my ammonia product is in grams, I can figure out how many of them there are in moles, and hence how many N2s I need to make them, and how heavy that is. If you notice that kilo was not used, it was not converted in this case. So my final set of units, everything else should cancel out except for that kilo. And then we have grams of N2. What numeric answer did you guys find? 16.4 sounds about right. Kilograms of N2. Could you find how many grams of hydrogen are required? Would there be anything different?
Not really, except changing N2 for H.
Use a different stoichiometric relationship, a different molar mass. All right, so I want you to be able to do forwards and backwards all these stoichiometric reactions. I'm sorry I went over today. I will send an email or announcement out confirming the location of Friday's exam review session. Thank you.